One of the topics that intimidate people in their high school mathematics is little surprising are logarithms. It's due to the part of how it is taught, and the other is how counterintuitive it feels first when we start to learn them. Even though we will discuss the basics of logarithms, this video is not an introduction to them, but more a building of intuition. Along with that, we will see how we use logarithms in our daily life even without noticing. Consider you have a n-folded paper handed to you. You unfold it once, doubling the size of paper. You unfold it again, quadrupling the size from initial. Let's say it was folded 3 times. The end result will be 8 times the size of the paper you have initially started with. In this scenario, we are doubling the paper each time we are unfolding it. In equation, we can denote it as 2 to the nth power equals 8, which as n equals 3 becomes 2 cubed equals 8. This is the process which is known to us as exponentiation. In this example, we can take 2 as the growth rate, the power as the time step of the function, and the resultant as, well, the result. Logarithm allow us to backtrack this process. Just like addition and subtraction are inverses of each other, logarithms are the inverse operation of exponentiation. If we have to find the log of 8 with the base 2, we will get 3. The base represents the growth rate, the 8 is representing the final result, and 3 is the time step. But as we were getting the resultant from power in exponentiation, now in log we get the time step as the answer. But why is this useful? Anywhere we need a scale that is fairly large, like in millions, you can take the logarithmic scale, reducing it drastically and making it much easier to manage. The log allows us to see the exponential growth of anything in a linear fashion. Like recently, we used it to plot the cases of COVID-19. Even a simple investment that gives you some kind of return can be calculated to see how much time you have to go to get the desired amount of money. The various laws and properties of logarithms arise due to this very fact of inverse exponentiation. You want to multiply two large numbers, take them into the logarithmic world, add them and take their exponent, keeping the same base as you took in the log, and you will get the product without even doing so. But let's go more personal. Let's talk about life. Have you ever experienced the passage of time? And I don't mean it philosophically, but the time being sped up as you grow older. Or sometimes the size of a purchased chocolate bar being smaller as it used to be a long time before, like in your childhood. Or even the way we choose items based on difference of a price. Let me show you what I mean. Consider you are buying a chocolate bar. It is priced at $5 and there is a new flavor priced at $10. Would you buy this new flavor? Probably not. Another similar scenario, you are purchasing a phone priced at $495 and you see a more superior model priced at around $500. Would you buy it? I think you would. If you compare these two scenarios, the price increase is exactly the same, but the overall price is pretty different. That makes us psychologically choose different things. This psychological phenomenon is called as Weber's law. Definition wise, it says that there should be a minimum threshold before we start noticing the difference in something. This threshold, however, varies with respect to the amount we are measuring. It could be the amount of sound volume or amount of price, as in our just seen example. Mathematically, Weber's law is given as delta I over I equals K. where I is the intensity, delta I is representing the change in the intensity. It shows that this fraction should be a constant k. This k varies depending on what you are trying to measure. For example, if you are comparing two weights in each hand, there should be a minimum difference between them. That can make you say which one is heavier. If they are very close, you might not be able to say. This actually changes based on how much we are measuring, which is given by the k in the Weber's law. But what pattern would this constant follow? Look at this curve. You might have guessed it, it's the logarithmic curve. I have made this interactive Desmos graph for Weber's law. The blue line can be interpreted as I, the intensity, and the green one as delta I plus I, the change in intensity. Look how it outputs the perceived intensity K on the y-axis. At 2 and 4, the difference is pretty noticeable. The same at 12 and 14 is negligible. This is Weber's law. By the way, I have linked this Desmos graph in the description so that you can go and play with it too. Market analysts use Weber's law all the time. They know how much to reduce the content of a thing like food item without increasing its price that you will not be able to detect. It has a term actually called as shrinkflation. This is the same reason why life seems to speed up as we grow. Even though the year is of the same length, we have experienced so many years as we grow up that everything just seems to pass by quickly. Just like our two sliders sitting negligibly on the logarithmic curve. In conclusion, even if logarithms seem counterintuitive at first, they basically make up all our experience of life. Visually, auditorily, even in the decisions we make. If you like this video, please consider subscribing for more content like this. Also, your feedback is dearly appreciated in the comments. Check the description for more related stuff to this topic. Till then, keep learning. I will see you in the next one.